to look at systems of equations and how these medieval Chinese mathematicians were thinking about systems of equations. So the first one I want to talk about. So in this video, I'm not going to talk about congruence equations or anything like that. I'm just going to talk about regular linear equations. And this is, I'm going to give a problem of the 100 fowls, which is there are three different types of birds. Each one counts. Each one costs a different number of coins. You spend a certain number of coins, and then you get 100 fowls. And from those pieces of information, you want to try to determine what are the possible number of fowls that you could get. So, the first one, it's something like roosters cost 5 coins. Some other ducks cost 3 coins, and then for chicks it's 3 for 1 coin, or they cost a third of a coin. Okay, so we've got something like 5x plus 3y plus 1/3 z, and in the particular formulation of the book, you spend 100, so 100 coins, and then you buy 100 fowls. So you have x plus y plus z is also equal to 100. Okay, now this is a system of two linear equations in 3 unknowns. So from just basic linear algebra principles, we basically know that from that alone, we know that there's going to be one of two things are going to happen. Either there's going to be no solutions, or there's going to be infinitely many solutions. Since these equations don't conflict with each other in any ways, they don't give contradictory requirements. Like it's not just this equation. Anyways, they're not contradictory equations. We know there's going to be infinitely many solutions. Now, obviously, there are going to be some restrictions on the types of solutions. They can't be negative, and they can't be fractions. So they can't be negative, and they can't be fractions. Excuse me. So, given that, we want to determine what are the solutions. Now, again, there's one way to think about this, which is just to forget about that restriction, solve it, and then impose that restriction on the end. I'm going to propose something different that is a little bit more in line with how this solution was given. So what I want to do is I want to assume that we can find some solution. We find some solution. X naught, so x is equal to some x naught, y is equal to some y naught, z is equal to some z naught. And now here's what I want to do. I want to, from there, I want to figure out if I have a solution, how I need to increment these values to get another solution. So I want something where it says like, well, if I have the solution, if you have any solution and you decrease x by this much, you increase y by this much, and decrease y by this much, or decrease z by that much, that's going to give you a solution. So in other words, what I want is I want the following to hold true. I want to find the increments, which I'm going to call delta x, delta y, delta z, such that when you plug the deltas in over here, you get 0. In other words, if you increment x by delta x, if you increment y by delta y, and you increment z by delta z, this left-hand side remains unchanged. And by the way, when I say increment, if the delta is a negative, that means decrement. Okay. And then similarly, I want those deltas to satisfy this as well. If you increment delta x by delta x, y by delta y, and z by delta z, this left-hand side remains unchanged. So in other words, that's equal to 0. So now what we're going to do is we're going to solve this system of equations. 5 delta x plus 3 delta y plus 1 over 3 delta z is equal to 0. And then delta x plus delta y plus delta z is equal to 0. Okay, so now our variables are delta x, delta y, delta z. Now, previously in the book, they explained that they actually had, there was a way that they solved systems of equations like this that was basically just a Gaussian elimination. And now I see that I'm off the screen a little bit here. Sorry, let me check. Okay, sorry about that. That they had a way to solve equations like this that were basically Gaussian elimination. So that's what I'm going to do now. I'm going to solve this. I'm going to multiply this equation by 5. I'm actually I'm sort of going to do Gaussian elimination, but not maybe in the most systematic way here. I'm going to multiply this equation by 5 and subtract it from that one. So 5 delta x minus delta x is going to be 0 delta x. So 3 delta y minus 5 delta y is going to be minus 2 delta y. And then 1/3 delta z minus 5 delta z is going to be 1/3 minus 5. So 5 is equal to 15/3. So it's 1/3 minus 15/3. That's going to be minus 14/3. Okay, and then we've got delta x plus delta y plus delta z is equal to 0. Okay, now one thing that I can do is I can, so there's going to be a free variable here because, again, just like before, there are 2 equations and 3 unknowns. So it's kind of, up to you what you want to do from here. What I'm going to do is I'm going to divide both sides of this equation by minus 2. And so we're going to have 2 delta y plus 7/3 delta z is equal to 0. Okay, so we can now solve this equation for delta y in terms of delta z. So this gives delta y, this equation gives delta y is equal to minus 7/3 delta z. So I'm just going to write it like this. Okay, and so now I can come down here and I can say delta x plus delta y, so that's going to be minus 7/3 delta z, then plus, I'm going to want to get a common denominator here, so plus 3/3 delta z is equal to 0. And now I'm going to get delta x, well, minus 7/3 plus 3/3, minus 7 plus 3 is minus 4. So delta x is equal to 4/3 delta z. Okay, so delta y is equal to minus 7/3 delta z, and delta x is equal to 4/3 delta z. So what I'm going to say, the problem, the nature of the problem suggests that delta z, the nature of the problem suggests that the z naught should be a multiple of 3. Whatever the solution is, it should be a multiple of 3. So z naught should be a multiple of 3. And if I want to maintain z naught being a multiple of 3, then delta z should also be a multiple of 3. And that's simply because 3 chicks cost 1 coin. Okay, and so if you can't break your coin into 3 pieces, you have to just, the minimal amount of chicks that you can buy is 3. Okay, so what this means over here is that I'm going to pick delta z to be the smallest number that is divisible by 3. And so you can see here, even though we're not dealing with congruence relations explicitly, all of those ideas are still present. So what I'm going to do here is I'm going to pick delta z to be equal to 3. I could literally pick any value, any real number for delta z is going to give me a solution to this equation here. But again, I want it to be, I want to do a couple of things. I want to make sure that z always stays a multiple of 3. And then I want to take these, given that, I want to take these the smallest step increments. So that means I need to have delta z be equal to 3, because that's the smallest multiple of 3, the smallest non-zero multiple of 3. Okay, So then if delta z, so I'm going to pick delta z. I know my work here is a little messy. I'm going to pick delta z here to be equal to 3. Okay, so then what this tells me over here is delta x is going to be equal to 4/3 times delta z, so that's 4. Delta y. Delta y is going to be equal to minus 7/3 times delta z, so that's going to be equal to minus 7. And then z, delta z is equal to 3. Okay, good. So now what this means is if you have a solution and you want to get another solution, you increment x by 4, you decrement y by 7, and you increment z by 3. And we can immediately see just by inspection that if you start with a solution, x naught, y naught, z naught, if it's a solution, you add them all together, you get 100, and notice that 4 minus 7 plus 3 is equal to 0. So in other words, if you go from one solution to another solution via adding these deltas, you're increasing the x and y, or x and z by a total of 7, by 4, and by 3. You decrease the y by 7, and so the total sum remains 100. And something similar is true if you change the x, y, and z by the prescribed deltas and plug them in on the left-hand side. That's also going to be 0, meaning the total cost here stays 100. Okay, so I'm going to erase this side of the board over here. Now all that remains is to come up with a solution. Coming up with just one solution to this, and maybe somehow like a minimal solution in some sense. Like what is a minimal solution? Maybe for like the smallest value of x for which we can have a solution here. So something like that. Okay. Well, let's say we try to look at this solution. Let's say we try to solve this, and let's say we want to take, say, x is equal to 0. So basically, it now becomes a system of equations, 2 equations in 2 unknowns. Okay, so remember, the having infinitely many solutions, as the book talks about earlier, is not something that was explicitly handled, right? But if we have one solution, that's okay. So if we assume that x is equal to 0, notice what's going to happen. It now becomes an equation, 2 equations in 2 unknowns. So then we're going to have 3y plus 1/3 z equals 100, and then we're going to have y plus z equals 100. And again, they know how to do Gaussian elimination. Obviously, they didn't call it Gaussian elimination. Gauss was way after what they were doing. But again, just because that's what I'm used to, that's what I'm going to call it. So if I multiply the bottom equation by 3 and subtract it from the top equation, 3y minus y here, 3y minus 3y will be 0. 1/3 z minus 3z, so 3 is 9/3. So 1/3 minus 9/3, 1/3 minus 9/3 is going to give you minus 8/3. And then over here, 100 minus 300 is going to be equal to minus 200. And now I want to figure out what z is here. Well, I'm going to multiply both sides by minus 1, of course. I'm going to multiply both sides by 3. So this becomes 600, and then z is going to be equal to 600 divided by 8. So 100 divided by 4 is 25. 200 divided by 8 is 25. So this is going to be equal to 75. Okay, so z is equal to 75. If z is equal to 75, this means y is equal to 25. Okay, so I can have one solution, x is equal to 0, y is going to be equal to 25. And then z is going to be equal to 75. So I'm going to call these x naught, y naught, and z naught. This is my first solution. Now what this means is if I increase x by 4, I decrease y by 7, and I increase z by 3, that's going to give me more solutions. And if I repeat this process over and over again, those are going to be the solutions that I get. Now, I didn't mention this before, but also if we multiply all of these by -1, that's also going to give us another solution as well. Okay, but notice that if we start at x naught equals 0, we can't decrease. So we're going to start this and increase and do these increments and see how many solutions that we get. So I'm going to say x0 is equal to 0, y0 is equal to 25, z0 is equal to 75. Now I'm going to increment x by 4. So then I'm going to call this x1, that's going to be equal to 4. y1 it has to decrement by 7, so 25 minus 7 is equal to 18. And then what I'm going to call z1, we're going to increment that by 3. We're going to get 78. Okay? x2 is 8. y2 is 11. z2 is equal to 81. And then finally, x3 is equal to 12. y3 is equal to 4. 11 minus 7 is 4. And z3 is equal to 84. Now we can't do this again because then we're going to end up with negative values of y3. Okay, now notice that when I solved that delta equation, I picked what delta z is. I needed it to be a multiple of 3, and I needed to be a multiple of 3 because I needed to make sure that if we start with a solution that's a multiple of 3 and we do this process, we're also going to get a solution that's also going to be a multiple of 3. But maybe you think, okay, well, let's think about what if you pick delta z to be something else? Like, what if you pick delta z to be 1? And you just did this process 3 times and kind of ignored those solutions where you got non-integer values of z. Well, if you think about it, if you just do that 3 times, everything's going to be off by a factor of 3, so you're just going to get exactly what we got here. On the other hand, you could say, well, what if you pick delta z to be equal to 6? If you pick delta z to be equal to 6, you're going to get like this solution and this solution, but you would miss those 2 solutions. Okay, so what that says is these are the solutions then that satisfy the criteria, that they satisfy this equation. That's like the equations that they solve, but then there's these sort of side conditions or auxiliary conditions that we have. We need them all to be integers. We need them all to be non-negative. Okay, and the other one that's kind of interesting that you don't typically see in things like this is that we want z to be a multiple of 3. At least the problem highly suggests that z should be a multiple of 3. If z is not a multiple of 3, again, then we have to divide up the coins. Now, if you don't have that restriction, that z be a multiple of 3, there's going to be more solutions. Okay, but if z has to be a multiple of 3, then these are going to be the solutions. Anyways, also, the other reason that z, anyways, I will, there's other reasons. The condition of z being a multiple of 3 is already kind of implied by things, but that was sort of the thing that helped me pick what delta z should be in that intermediate step. Anyways, that is it that I'm going to look at for solving systems of equations like this. Actually, no, sorry. There's one more important thing that I meant to mention. My apologies. I should really prepare for these videos before I make them. One of the things that I want to mention is this procedure that we just went over is a very standard linear algebra procedure. Okay, because what we begin with, I'm going to kind of write this in matrix vector notation, or not kind of, I'm going to write this in matrix vector notation. We can write this as mv is equal to b. Now, a very common conceptual framework for solving non-homogeneous equations like this is to first solve the corresponding homogeneous equation. We'll say this solution is VH, and then find a particular solution to MV equals B. We'll call this V sub P. Then any solution to this non-homogeneous equation can be written in the form V is equal to the general solution to the homogeneous equation plus a particular solution. Now this is typically used when this system is underdetermined. And in other words, there are more unknowns than there are equations. You just find any solution to this, let's say by Gaussian elimination, and then you solve this. Now, if you do Gaussian elimination on this, you're going to be able to write the solution in this form here, right? But this, what I'm saying is, the framework that they were using is essentially the same standard framework that we use. And the way they explained it, I think, is very helpful, because what you have is this idea of starting with a solution that's good, and then instead of just looking at every solution that you would get if you just applied this method right here, and then trying to figure out which ones are going to be integer solutions, I like this idea that he has described it as each time you increment the number of roosters by 4 or whatever it was, the number of chickens, you decrement the number of chickens by 7, and you increase the number of chicks by 3. I think that's a very helpful way of looking at kind of integer equations like this. Anyways, we're going to be looking at congruences in upcoming videos, but that's it for this sort of, this is one look at linear equations that they solve. And I hope you look at I hope you read about how they sort of did their matrix. I mean, they basically were doing matrix manipulations. So I hope you are able to read that, and I hope that you find it as interesting as I did.